The assessment procedure proposed by PERPETUATE project is based on 3 steps. In the first one, building is classified depending on its most probable seismic damage. Then safety and conservation requirements are discussed and the seismic hazard is defined. Finally, structural information is collected and material parameters are investigated. In the second step, all data are used to model the structure and evaluate its seismic safety. At the end of the process, on step 3, rehabilitation decisions are taken on the basis of the results achieved in previous steps and by expert judgment. The classification is based on the identification of most relevant macroelements and prevailing damage modes. The assignment to a class drives the choice of models to be adopted to describe the seismic behavior of the building. In case of ordinary buildings, performance levels are usually associated to earthquake consequences like costs of repair, safety of people, usability, and operational requirements. In case of cultural heritage assets, they have to be linked also to cultural relevance concepts. To this aim, in PERPETUATE project, targets related to use and human life, building conservation and artistic assets conservation have been considered. For each of these aspects, different performance levels are associated to increasing expected hazard levels. Once safety and conservation requirements have been defined from a conceptual point of view, proper acceptance criteria have to be established in order to verify whether the structure is able or not to satisfy the required performance level. To this aim, the damage level is used and directly correlated to the building and artistic asset performance levels. Seismic demand, expressed in terms of return period, is then defined for each considered performance level. Finally, according to the performance-based approach, the fulfillment of each specific performance level is verified by considering the corresponding earthquake hazard level, defined by annual probability of exceedance or return period. The considered return periods may be modified by introducing some coefficients which are aimed to take into account the use and architectonic and artistic relevance of the examined building. Seismic hazard is the study of expected earthquake ground motion at the surface. The results are represented as seismic hazard maps, which identify the motion of different areas and characterize the seismic input for the assessment of expected damage to cultural heritage assets. By considering historical seismicity, geological evidence of crustal faults, earthquake sources and related magnitude and distance, and by selecting proper ground motion prediction equations, probabilistic seismic hazard analysis provide the relationship between ground motion values and their annual probabilities of exceedance or return periods.
I'm Hormuz Modarisi from BRGM, France. BRGM is the Geological Survey of France, and we have been involved in PERPETUATE project. And one of the works we have performed was on the hazard assessment for historical monuments. Historical monuments have some particularities regarding the hazard assessment. Amongst them, I would say, for example, that the return period is one of the important issues for the hazard assessment. The other issue comes from the brittle behavior of historical monuments, essentially made by masonry, and that involves some studies about, for example, different components of earthquake to be considered, not only the acceleration as is used usually for normal buildings or different types of modern and critical structures.
Perpetuate has considered not only the problem of shaking, but also the effects of fault rupture dislocations on monumental constructions. In this case, severe damage may occur, not due to seismic acceleration, but to sudden static settlements at foundation level.
Hello, my name is George Gazetas. I'm a professor of civil engineering at the National Technical University of Athens, one of the participants in this project. Now, one of the questions we had to answer is how our monuments can survive on top of a major tectonic fault. Now, earthquakes are produced in such tectonic faults. They don't always propagate all the way to the surface, but sometimes they do. And when they do, and a monument or any structure finds itself on top of this rupture, severe consequences will ensue. It will be subject to very large displacements, rotations, and of course, old monuments were not prepared for this. They were not designed at all, let alone for this type of motions. And even worse, the current codes don't have any advice as to what to do in these cases. So we have to resort into analysis, simulating the fault rupture as it is shown in this here, which when arrives underneath the structure, there is an interaction with it, and it may or may not survive depending on the characteristics of the structure. We are trying to understand the mechanics of this interplay between fault, soil and structure, and eventually to find means of defending against these displacements. Now, in addition to that, the shaking near such fault motions is not only very severe, this everybody understands, on top of the fault, but it is very peculiar. It has some characteristics which were only recently discovered, and we're trying to find out how the monuments, how this type of facilities with their brittleness and the other characteristics will behave during these peculiar strong motions. And you have to take into account that around the European areas and the other Mediterranean areas, there is always this type of danger. In Greece, in Turkey, in Italy and Algeria, very often faults do rupture all the way to the surface with all these other negative consequences. So our task will be to provide means of helping the monuments against these cases.
The response of historic masonry buildings subjected to tectonically induced ground distress was studied experimentally and analytically. A simple yet representative soil foundation masonry wall system was considered. A hybrid two-steps methodology was adopted to rigorously account for the multiple response nonlinearities both in the soil and the superstructure and predicted the associated wall damage. Results highlight the determinative role of the exact location of the structure with respect to the fault. Moreover, the effect of foundation characteristics on the system performance were studied thoroughly in view of 3 different plausible foundation types. The seismic safety assessment of an existing building is affected by more uncertainties than the ones related to the design of a new building. In fact, epistemic uncertainties due to the incomplete knowledge of the asset add up to the statistical ones. In order to treat properly these uncertainties, built information process represents a fundamental step.
As built information according to perpetuate methodology consists of several steps. The first one is preliminary knowledge of the building that actually relates to the geometry, mechanical parameters and ranges that are related to. The second step is getting historical data on transformation and damage evolution. especially related to earthquake problems and damage that was provoked due to previous seismic actions. The third step is basically very close to the second one, and that's state of maintenance and damage mechanisms identification, which is characteristic for different architectonic assets. The fourth step is already a preliminary numerical analysis in order, which we call it sensitivity analysis, in order to determine which are the main mechanical parameters that should be focused on and that are determining the overall response of the building. Then, according to that sensitivity analysis, we go to the design effective investigation program. That actually, again, depends from the size of the building, the different periods that it was built, and it comprehends the numerous destructive tests, manic-destructive tests, and non-destructive tests, especially for the values of high artistic values, where we have some mosaic or fresco, and we cannot reach behind that. So we have to apply different non-destructive tests and then to cluster all their data results in order to get what is the state of the structure behind the artistic value. And at the last, if it's possible, it's always advisable to do an ambient vibration test in order to identify structural model and to verify our numerical model that we prepare for this particular asset.
Thanks to PERPETUATE project, we have a numerical model able to take into account dynamic interaction between the foundation of the monument and its surrounding soil. This dynamic soil-foundation interaction may modify significantly seismic response of the historical structure. The simplified numerical soil foundation model developed by University of Thessaloniki takes into account soil foundation flexibility and interaction effects and produces results ready to be used by other numerical software for seismic assessment of cultural heritage assets. Until now, when engineers simulate in practice seismic response of monuments, they neglect the existence of the foundation soil or assume that the foundation is very rigid, exactly as they do for modern structures. In reality, though, the dynamic response of the foundation of the monument is affected by the response of the surrounding soil. This soil-foundation interaction certainly influences seismic response of the whole historical structure. Moreover, monumental foundations are naturally deteriorated throughout the years, thus characterized by discontinuities and reduced stiffness. For these reasons, it is very important to take into account the correct or actual soil foundation properties in procedures for seismic assessment of cultural heritage.
The final aim of the performance-based assessment of an architectonic asset is the evaluation of the maximum return period of the seismic input that is compatible with the fulfillment of a given performance level. The comparison with the target earthquake hazard levels gives a measure of the safety of the building. If the maximum return period of the seismic input is greater than the target one, the asset fulfills the required performance. Otherwise, some rehabilitation decisions are necessary. In order to calculate the maximum return period of the seismic input for the considered asset, the nonlinear response of the building has to be investigated in terms of relationship between force and displacement up to collapse. Different modeling approaches may be adopted, depending on the type of asset. The macroelement approach is suggested in the case of assets made by single macroelements. For complex assets made by many macroelements, the approach depends on the type of seismic behavior. For assets that behave as a box, a global approach may be adopted, while in other cases, the subdivision in macroelements with independent seismic analysis is preferable. Different methods of nonlinear analysis may be adopted. The pushover analysis and the consequent evaluation of the seismic demand by the capacity spectrum method is the standard approach to be adopted. For some classes, nonlinear dynamic analysis may be considered as well. A reliable assessment depends on the capability of the adopted vulnerability model to describe the seismic response of the asset. Thus, the choice of model is a crucial step. 4 different approaches may be used as a function of the different architectonic asset classes and prevailing seismic response. This table shows the standard methods proposed by PERPETUATE for the 7 classes of architectonic assets. Sometimes, more than one method is employable as a function of different architectonic characteristics and complexity of the asset. The last but fundamental step of the assessment procedure is the definition of performance levels on the basis of results provided by vulnerability models. Through this aim, an innovative multi-criteria approach has been developed, which takes into account damage levels evaluated at the different scales of the building, damage in each single structural element, seismic capacity of each macro element, and behavior of the whole asset. In case a safety verification highlights the need of improving the seismic capacity of the building, different rehabilitation alternatives may be considered. The design of strengthening intervention is not the only possible choice. Conservation without intervention may be also considered if strengthening intervention would be too invasive. In this case, the usable life of the building is evaluated and further decisions are postponed. Another alternative is the revision of safety requirements that, in practice, means the change of use of the building. Finally, the building may be monitored and models upgraded. Also in this case, the choice is forecast in the future when more accurate and validated tools will be available. PERPETUATE project has developed procedures not only for the analysis of single monuments, but also for the important problem of seismic vulnerability and risk assessment of aggregated buildings in ancient urban centers.
For a local authority, it is essential to forecast losses over the entire territory to properly budget and program interventions. Hence, it is very important to define seismic vulnerability at this scale, not just from a structural point of view, but also from a cultural and economic point of view. The problem in general is that within an urban territory, there are many different assets of diverse age, value, quality and structural capacity. A procedure that would be able to assess the seismic vulnerability of all these assets at territorial scale needs to be flexible and comprehensive at the same time. Within the PERPETUATE project, we have developed 2 procedures which starts from the urban scale and then focusing to each building to define their characteristics, both from a structural point of view and from an architectonic point of view, and define connections so that we can understand better their seismic vulnerability. Because we can consider situations in which the territorial assets are either in their conservation states or they have just been affected by a seismic event, such as the case in L'Aquila in 2009, we have developed 2 parallel procedures, the FAMIVE procedures and the LOG-IDF procedure. The first is related to assessing the capacity of the building. The second is related to documenting the damage and interpreting the level and type of damage in order to understand better the seismic behavior, so that the 2 procedures are actually able to complement each other. They are based on the same data collections, and so that we can compare both input data and results. And they allow us to develop fragility curves which are based directly on the data on site, so they are not theoretical reference. And in this way we can compare, for instance, the cumulative distribution of a particular type of damage, collapse rather, so that we can, with reference to an expected scenario and return period of a given event, define how many of these buildings will be damaged and to which level they will be damaged. This will then allow us to define and make some decision about rehabilitation, in particular considering alternative strategies for that we can implement on different buildings, quantifying the fragility curve shift that each of the strategy would entail, and hence reconsider losses for different strategies of intervention and the and implement cost-benefit analysis, eventually defining plans for the implementation of the rehabilitation, so that this type of picture becomes an image of the past.